Okay, it's 4 o'clock, so let's begin here. So we will discuss project number 4 today, and also we'll go through this PowerPoint presentation of mine that discusses some research that I've done involving Bootstrap. Are there any questions before we get started here? Okay. Pretty. 95% confident. Was that okay? Okay. I want to get it done before Thanksgiving, and I want to get it done after Chapter 5, but not including Chapter 6. And right now, it looks like we'll either finish Chapter 5 here, or we'll finish Chapter 5 this day, but there wouldn't be a whole lot to do. Okay, so let's talk about this presentation. So, as I think I mentioned once before in this class, normally when I've taught this course in the past, I always have my students read a paper from the statistics literature that uses the Bootstrap, and then they present the paper in class, replicating the results in the paper. Present the paper in class for about 25 minutes. Given that at the beginning of the semester we had about 11, 12 students, this would translate into then 4 whole class periods for everyone to give the presentation. So knowing that before getting into this class in late July and early August when I was starting to do some prep work, I decided that probably wouldn't be the way to go. And then I had the idea of, well, how about I actually present a paper to you and have you reproduce the results for a project? And so that's essentially what we're going to do. And since I'm presenting the paper, I might as well present one of my own, place where I've done some research involving the Bootstrap. And so that's the motivation behind doing what we're going to be doing today. And as I mentioned before, this is actually from my 2003 interview here at Nebraska, when I was hoping that they would hire me. And most of this presentation involves this particular paper, I should say, that was published in Biometrics in 2004. Just to, I guess, give you some background here. Typically, when people talk about statistical research journals, there's a first tier, second tier, and then some other stuff. Biometrics is typically thought of as the first tier journal, so I was quite happy when I got it published there. First tier journals, there's typically 5 that most people agree on: JASA, Biometric Hub, Annals of Statistics, Biometrics, and JRSSB, which is Journal of Royal Statistical Society, Series B. So those are the top journals. Typically, if you get a paper published in one of these journals, you are satisfied with it. You're not wishing, oh, I wish I would have got it into some other journal. So that's why it's typically thought as a first-tier journal. So anyway, and this research was actually funded by an NSF grant that I got. I've actually gotten 2 NSF grants where I've been the PI on this area of research. I don't actually, I kind of stopped doing research in this area. Just in some respect, I kind of needed a break from it. And now most of my other research that I do right now is in an area called group testing. But still, it's an interesting research area. In this PowerPoint presentation, I'm not going to do all of it, as I mentioned last time. Just give you enough background into what the problem is so that we can get to the most important part for this class, the Bootstrap part. But it will take some time to get there. This presentation, too, it has too much animation in it. If I were to do it again, I wouldn't do it this way. We have to put it in the context of what it was like in 2003. Most statisticians were not using PowerPoint. Rarely, you wouldn't see a PowerPoint presentation a whole lot. Typically, people were still printing off slides on a transparency and using an overhead projector. There were still some holdouts out there who were actually writing by hand their presentations on transparencies. Fortunately, I never did that. You would sometimes see on airplanes going to JSM, stat professors writing out their presentations still on transparencies. Meaning that they hadn't really prepared before they actually got on the airplane and were going to JSM. So my son would say, sad choice. Now, whenever you give a presentation, of course you should have some kind of icebreaker, some kind of motivation and stuff. And I decided to do more of a little bit of an icebreaker here for my presentation. I just couldn't take this picture out of the presentation to show you guys. But this is, so, I got my PhD from Kansas State, and here I was interviewing at UNL. And at the time, Huskers and the Wildcats were big rivals in football. And I wanted to make sure that people knew where my allegiances were for this presentation. So I put this little picture in my presentation, and this is actually a picture of me in 1999 in front of Memorial Stadium on the east side. Back before they were doing the construction work, and they had this great statue out in front of Memorial Stadium. I don't know, where is it now? So I know it's not there now. Does anyone know where it is? Did they put it in a storage?
Storage until the construction's
okay. But anyway, this statue was made to resemble a picture taken by an actual newspaper, taken during, I think it was the 1995 Nebraska K-State game. So even though this is, you can't see it here, there's no power cat here, this is actually a K-State football player. And so I wanted to help emphasize, again, my allegiances towards Nebraska, so here I am helping to tackle this K-Stater. Anyway, it got laughs during the presentation. We're going to talk about something I refer to as multiple response categorical variables. This term is used in a number of different ways in statistics. The way I'm going to refer to it is in reference to survey data, where often you see on a survey a question that asks, choose all that apply from a set of predefined responses, or pick any responses from a set of predefined responses. Maybe C, just to be general, C predefined responses, or let's say items. And again, you can call these multiple response categorical variables, or MRCVs, because one could pick more than one response, multiple response, and you're picking from categories. In the non-statistical literature, in particular psychology, sociology, and marketing, you'll hear these referred to as pick any out of C data. So the slash there means out of. And the corresponding variables that would summarize this kind of data are called pick any out of C variables. The earliest reference to this I have found is Coombs in 1964. It's actually a textbook. And the motivating then data example that I used for this presentation involved a survey of 279 Kansas farmers that was conducted by the Department of Animal Sciences at Kansas State. One of the questions on the survey asked these farmers, what are your primary sources of veterinary information? Pick all that apply from these 5. So they could pick 1 of these responses, they could pick 2, they could pick 3, 4, 5, or in fact they could pick none. So notice how this differs from the way that we normally think of, survey questions, where you would choose 1 out of, let's say, 5 possible categories. That's the normal, but I'm sure probably most of you have seen these kinds of questions before, where you choose all that apply or pick any. Oftentimes, you will hear people say, don't use those kinds of questions. And the reason being is they don't know how to properly analyze it. Until, I guess, my research. Another question on the survey was, what swine waste disposal methods do you use? Pick all that apply from these 4. Again, they could pick 0, 1, 2, 3, or 4 possible different responses. Now, in situations like this, people will want to summarize this type of data in a table-like structure like this. You normally would think this as kind of a contingency table, where what we have here, again, on the rows, oops, don't mind, that was strange. Why would a white pen come up? No, I don't want yellow. No, let's just do black. It'll be boring. So we have waste storage method on the rows, sources of veterinary information on the columns. And so what this means then is 34 farmers use Lagoon as a waste storage method and professional consultant as a source of veterinary information. 54 use Lagoon and veterinary. And so that's a table representing, our responses in our survey. But what makes this different from the usual kind of contingency table is that farmers can be represented in more than one cell table. Typically, a survey respondent would only be in one and only one cell. Here, we could actually have a farmer pick all waste storage methods, pick all sources of veterinary information, and be represented in 20 different cells. So now, hopefully, you're starting to think, okay, maybe there's some kind of extra dependence that you have to worry about. Indeed, that's what makes this research problem interesting. This table here, though, can actually, I'm going to actually refer to it as a marginal table, because it's actually a marginal representation of another way to view the data that you'll see later. But given a table structure like this, a natural question that you would want to ask then is, well, are the sources of veterinary information and waste storage methods independent? Typically, we ask these kinds of questions with in situations where we use a Pearson chi-square test for independence. But in this particular case, since a survey respondent can actually be in more than one cell, you should not use a regular old Pearson chi-square test for independence. So that's why this was an open research problem. What do you do? How can you answer questions like this? So what I'm going to talk about is, in this particular case, how you can construct a test. We're going to use the Bootstrap to do it. Let's see here. So, like I said, I'm going to skip through certain things that are not really necessary for what we're doing here. I do want to mention this, is that, these pick any or choose all apply questions appear in many, many different places. In particular, one that probably all of you have encountered is with the census, starting with the 2000 census. The ethnicity question was choose all that apply, just to represent our multiracial background that many people have, including our president. So I guess it was just in time that they got this on the census, obviously since Obama has a multiracial background. So the goals of this NSF grant, and also my second NSF grant that I got, was to develop parallel, similar methods to the stuff that you normally do with categorical data analysis, but in the context of these choose all that apply data, multiple response categorical variables. And we don't need past research. So let's start defining some notation then. Put this into a context that all of you, can better grasp. What does this data look like, and how do we work with the random variables and stuff? So I want to test for independence between two MRCDs. This is actually a marginal test of independence, and you'll see why as we go along. So let's let W and Y denote our MRCDs of interest. So in this case, let's let W denote the row MRCD, swine waste storage method, and Y denote the column MRCD, sources of veterinary information. Let's let W sub I, for I equal 1 to R, denote the row variable specific items that you can pick from. So for example, W1 is lagoon, W2 is pit, and so on. And now I'm going to use a 1 to note that that item was picked, 0 if it wasn't. So if someone uses lagoon, W1 is equal to 1. If someone doesn't use the GUI, W1 is equal to 0. Simply put. So 1's a positive response, 0 is a negative response. We can define Y sub j in the same kind of manner as well. And so this is what we get. A vector of correlated binary responses. So all of you, well, probably many of you have heard of correlated binary data. This is what we have. Correlated binary data was a real hot research topic starting, I guess, in the 1980s and going through the 1990s. Really a big topic of interest. Stuff like generalized estimating equations was developed in this context as well. Random effects models, generalized linear mixed models, I should say, were developed often in this context to solve these kinds of problems. So what we have here is that a person is contributing R plus C different binary responses, where what we've done is we've partitioned out these binary responses into row binary responses and column binary responses for our data. Let's let pi sub ij be the probability that wi is equal to 1 and y sub j is equal to 1. So in other words, it's just a joint probability between a row item and a column item in my table. Pi sub I dot just focuses on a particular row item. Pi sub dot j just focuses on a particular column item. Then this leads to then a set of hypotheses that would be of interest in this kind of a setting. If I want to test for marginal independence between W and Y, I can do the following. And this set of hypotheses should kind of look familiar. Pi sub ij is equal to pi I dot times pi dot j. For all the rows, for all the columns. It should look very familiar because it's close to what you have for a Pearson chi-square test for independence. Just got to, in fact, you can often write your hypotheses just like this, but you have to remember I have a slightly different form of a contingency table. The alternative is at least one of the equalities is not whole. And I call this a test for marginal independence because we're only concerned about Wi and Yj, those relationships. I don't care about, let's say, Wi and Wi prime. I don't care about that at all. I don't care about, let's say, a three-way relationship. I don't care about that. But when you see a table of responses like what we did before with that marginal table, the natural way that what you are interested in is let's say one row independent of a particular column. And so this is a way to approach that kind of a problem. Alan Agresti and Ivy Liu, in a Biometrics 1999 paper, really scared me, thinking that I no longer had a dissertation topic. So I was just starting some research on actually a simpler version of this kind of topic here, or I guess related stuff to what I'm presenting here. And in summer 1998, Agresti sent my advisor a draft of this paper, and he was quite scared at first before reading. It's like, uh-oh, have we been scooped? That's obviously not good when you're beginning your PhD research. Somebody else has already did what you wanted to do. Fortunately, though, what they were doing was a different approach for a problem that was actually kind of a follow-up to a paper that my advisor had in 1998 in the biometrics paper. But towards the end of the paper, they basically mentioned those hypotheses I just showed you on the previous slide as potentially this would be of interest to do. We're not doing them in this paper, but this might be a nice little extension if someone looked into it. And they called then this set of hypotheses simultaneous pairwise marginal independence. Well, why? Also, so they also suggested ways to approach the problem, but they didn't actually ever investigate them. And their approaches, a lot of them don't work out very well in the end. The reason why they call it SPMI is because independence is basically simultaneously being tested in RC 2x2 tables. Okay. To help explain that, here's my marginal table once again. And what we can do is focus on professional consultant and Lagoon. And what I've done is written out not only that 34 response that we see there, which would be positive response to professional consultant, positive response to Lagoon, but also I look at negative responses as well. And in fact, what you could do is write out a table like this for all of the all 20 cells in this table. You could write out a 2x2 version. And so what ends up happening then is a test for SPMI, those hypotheses that we saw before, can be equivalently expressed as a test in each of these 2x2 possible tables. There's 20 possible tables. Simultaneous, because you're doing 20 of them. Pairwise, because we're looking at pairwise combinations of the W's with the Y's. Marginal, because this table here is actually a marginal representation of something I will show you very shortly. And then independence. Now, you can also represent this in terms of odds ratios as well. Now, if you haven't had a categorical data analysis class, maybe you haven't looked at odds ratios before, that's okay. But I know none of you have had categorical class, so I'm going to still cover this. You don't need to know what odds ratios are exactly in order to do our corresponding project. But here's one of those 2x2 tables again, now written in terms of our notation here. So the typical way that we would form an odds ratio, again, is just to take the product of these two, divide by the product of these two. So here's my odds ratio for W and Y, ith W, jth Y. And so what SPMI represents then is that all these odds ratios then are equal to 1. Okay. Now there's another way to view the data. And this is what I refer to as a joint table. Again, on the rows we have W. On the columns we have Y. Show up very well. Y. And W and Y are combinations of binary variables. So that means then, since there are 4 binary variables here, there are 2 to the 4, or 16 possible combinations. I'll do a different pen color so that we can't see it. Y has 5 items, so that means there are 32 possibilities, 32 possible combinations. And so what one could do, let me mention this too. Every farmer is represented once and only once in this table. Because a farmer is going to only have one particular combination of the W's and one particular combination of the Y's. So because of that, we could actually use a regular Pearson chi-square test for independence on this table. But you have to think about what this is testing. This is testing these kinds of combinations of the row variables with these combinations of the column variables, but these combinations actually may not really be of interest to someone. I mean, who cares if it's 1, 0, 1, 0? What, is that really meaningful? Or is it more meaningful to say Lagoon is independent professional consultant? I think the latter. Also, what's interesting here, so this is a big table, as you can see. What's interesting here is that look at all the small cell counts. In particular, look at all the zero cell counts. And if you have a categorical background, you know when you have small cell counts, especially zero cell counts, you are going to have problems. You know, like high-score distribution approximation to a simple Pearson test statistic here is probably not going to work out very well. So I asked the question, then why not just test for independence in this joint table? I've already kind of given you reasons why not to. But also, what one can actually prove is that this joint independence actually implies SPMI. So if you have joint independence, you will get SPMI. But the reverse actually is not true. So it's kind of interesting that that happens. The reverse is not true. Also, the number of parameters under independence. For SPMI, there are R plus C. Why? Because remember, we're setting pi sub ij equal to pi I dot times pi dot j. There are R of these, there are C of these. So you only have R plus C parameters. For joint independence, though, you have 2 to the R rows, 2 to the C columns. You have a lot more parameters to deal with. The more parameters, the more difficult the problem can be. And indeed, that's what ends up happening. So sparse joint table is the norm in these kinds of settings. So that's why, again, more reason why we don't want to do that. But let's look at the relationship between the joint table and marginal table. Will help you see things here. So again, a farmer picks an item as a 1. A farmer does not pick an item as 0. Here's a table that we saw before. Here's my marginal table. It's called a marginal table because it's a marginal representation of this joint table. So for example, this 34 here is actually just the sum of these counts. Why? Because here's a positive response to professional consultant, positive response to Lagoon. Match those up, add those up, and you get 34. So that's the relationship between the two. Why we have a marginal table, a marginal test for independence. You could go further and examine the relationships then between the table. I'm not going to get into details. This is another part I'm going to skip over. But basically, if you let tau sub GH be a probability in the joint table, Gth row, Hth column, you can show that you can find a linear combination. Sorry, I know that's kind of low, but you at least can see it on here. You can see that each of these pi sub ij's is just a linear combination of particular taus. How do you get those? Well, you do some chronicle products, get the right kinds of matrices, it all comes out. Okay. So now let's talk about how we can test for SPMI. My advisor, Tom Logan, had some ideas. He didn't necessarily have time to write them up in a full paper, but he had some ideas. So he kind of just wrote them out in a technical report. And he suggested to do the following. Let n be the sample size. Pi hat sub ij be the number of positive responses to wi and yj divided by proportion of positive responses to row I, column j. Pi hat I dot, pi hat dot j are the similar row and column marginal estimated probabilities. So that, for example, pi hat 1, 1 in this particular situation would be simply 34 divided by 279. Okay? Pi hat 1 dot would be 34 plus 109. This right here. Divided by 279, you get 0.51. With that, then, we can take a look at a test statistic. You know, form a Pearson-like statistic, like you would normally. Take what the estimated probability is, subtract off what you would estimate it to be under the null hypothesis, square it, divide by the estimated expected probability under the null hypothesis. And we multiply by n there. This is just a different form of the Pearson statistic. I sum over all the W items and all the column items. Call that x squared m. Okay? Unfortunately, there was a problem. This problem, my advisor actually had a very similar statistic in his 98 biometrics paper for a slightly different problem. And so that was what motivated him to do this x squared m. But in Agreste's and Liu's 99 biometrics paper, they found a flaw in my advisor's reasoning. And that is this. The test statistic is not invariant to how positive responses are summarized. What I mean by that is that what happens if we switch the definition of positive to be a 0, negative to be 1? What ends up happening is your x squared m is going to be different. That's not good. You know, if you told a subject matter researcher who's interested in a problem like this that, you know, it's very important if you choose 1 to be a positive or 0 to be a positive response, because you can get different results, that subject matter researcher probably will never talk to you again. Because you don't want your decisions about a particular problem to change just how you code the data. Also, you can think of it this way. Perhaps instead of choose all that apply question saying choose all that apply, maybe it says choose all that don't apply. And you still keep a 1 for a positive, 0 for a negative. Again, your test statistic will change. The test statistic's not invariant to this arbitrary designation. So just to emphasize the point then, here's our original marginal table in x squared m, shown there, 28.27. Now, if I, and this is where that 34 comes from in that 2x2 table. Now, if I change everything to now, or if I change my, my column to be sources of veterinary information not chosen, so notice how you have a 109 here, here's the 109, now my test statistic becomes 11.52. And I can keep on going here. So now waste storage method not chosen, source of veterinary information chosen. We get a value of 16.44. Now, both of them not chosen, I get a test statistic of 6.08. Not good. And just to emphasize how this is a problem, some other competing researchers who were researching the same problem as not Agreste and Liu, but some other competing researchers who were also researching the same problem. Probably about 2002, 2003, they came up with a way to actually approach this problem here, and I happened to be the referee for it, and I said, well, your test statistic was not invariant, and the paper was rejected because of that. Okay. So what can we do? So here's our test statistic that we're going to use. I call it a modified Pearson statistic. Well, you know, if I have 4 possible different statistics that I could have, I'll just sum them together. Seems reasonable. That way I don't have to worry about it. You know? Sure. So let's sum them together. So here's our 2x2 item, the 2x2 table that we saw before. So my advisor's original recommendation then was this x squared m, written here. And what I'm going to, and notice how that focuses on the orange cell. That's what's really focusing on in that table. But then if I go to the next orange cell, I could form the exact same kind of statistic. And then I could keep on going to the other 2 cells in the table, and here's my statistic. That's invariant. Some nice math stuff happens. And everything simplifies down to a one term. Sum bound page 20. So that's nice. But it even gets nicer. Basically, one can show then that this statistic is just R times C different regular old Pearson statistics formed for each of those 2x2 tables. Sum them up. That's it. So for each of those 2x2 tables that we were seeing before, if I just simply call each of them x squared s sub ij, or w is I, y is the j, calculate each one. So in our Kansas farmer data, there would be 20 of them. Sum them all up. I get the statistic that was on the previous page. So here's examples of the 2x2 tables. Here's my test statistic, which I call x squared s. The s there is for sum. This is the test statistic that you're going to have to calculate for the project. You will need to write a function that calculates x squared s and x squared s sub ij for the project, for the Kansas farmer data. I strongly recommend that you take this approach to do the calculation. The reason why this is especially nice is that, as in most software packages, there's going to be a function or procedure that calculates a Pearson chi-square test for independence. So all you need to do is call this function over and over again for each of these 2x2 tables. That's it. So it's great that I have this test statistic. So do you think large or small values are going to indicate evidence against SPMI? Large. Okay. Now how large? Well, that's where we need some kind of distributional approximation. So you might think, well, each of these x squared s sub ij's are distributed chi-square 1 asymptotically, right? Okay, do approximate there. Chi-square 1. So maybe, the sum of independent chi-square 1 random variables is what? If we have r times c of them. Chi-square rc. You learned that in step 883. So perhaps, naively, we could just treat each of these x squared s sub ij's, we could treat them naively as independent. And then x squared s could be approximated by chi-square rc. Boy, that would be great. But it's not that easy. Also, you can say reject SPMI then if it was greater than 1 minus alpha quanta from this distribution. But these x squared s's sub ij's are not going to be independent. Because remember, every farmer in our data set, every farmer contributes a response to each of those tables. So you have dependent statistics here. And this is why the Bootstrap makes this, why this makes this an interesting problem for the Bootstrap. This is not necessarily an obvious way to approach this. But what one can do is actually derive an asymptotic distribution for the statistic. We're not going to get into it in too much detail because it's just not worthwhile spending our time on it. But I just want to briefly mention it and relate this to some other stuff that you've had in another class. What the asymptotic distribution of x squared s is it's a linear combination of independent chi-square 1s. A linear combination of chi-square 1s. Specifically, this is what one can show. This is my paper. X squared s converges in distribution to the sum I equal 1 to r times c. Here's my coefficient on the linear combination. And this x squared I represents an independent chi-square 1. Okay. Here are some of the details behind where these lambdas come from. They're actually eigenvalues of a matrix D inverse sigma. Here's D, here's sigma. Now, in your if you've taken Stat 870, you've seen stuff like this. What's this often referred to? Quadratic form. Okay. If Y is distributed multivariate normal with covariance matrix sigma, what's the distribution of this quadratic form? So this is distributed chi-square. If what? If what? It's not just A. Excuse me?
Y is a vector.
Yeah, Y is a vector. Yeah. So, typically you see people draw lines under it when you're referring to vectors, when you can't bold it with handwriting. Is symmetric idempotent? Does that look right? Okay. All of you should have seen this in a Stat 970 class if you've taken that. What happens, though, if A sigma inverse is not symmetric idempotent? Did you talk about that case? I did in my class, but it wasn't talked about that much. And I know when I was doing this research, this came up actually during my dissertation too. Like, oh, why didn't my professor talk about this more? Because this is so important. What happens if it's not symmetric idempotent? Never talk about it. Well, the eigenvalues of this, if you have a symmetric idempotent matrix, can someone quickly calculate the eigenvalues for me? Tell me what they would be. One. There can be some zeros if sigma is not full rank. So ones. Okay. So it actually, let me actually get out a different color here because it's just hard to write. Hard to see. So actually, this distributed sum I equal 1 to however many the dimension of y in terms of vector dimension. Lambda I xi squared, where xi squared is independent chi-square 1. And sum of independent chi-square 1s, then is chi-square, let's say r times sigma. So basically, now in an asymptotic setting here, I can write this as a quadratic form, and I get the same kind of things happening. But my lambdas are not equal to 1 because I don't have symmetric idempotent. So that's interesting, I think. So what could I do then? How could I use this asymptotic distribution? Well, perhaps you could estimate the eigenvalues. Put in estimates for D in sigma. But let me tell you that it doesn't end up working out that well. Remember that joint table that we saw, how big it was? That causes some of the problems. Alternatively, what you could do is maybe some kind of approximation to the actual asymptotic distribution. You can do what are called first order or second order Rouse-Scott adjustments. A first order Rouse-Scott adjustment says, let's adjust my statistic so that this has an expected value of R times C, which you would expect if I did actually have independence and I had a chi-square RC. And what ends up happening is that this is actually what's called a self-correcting statistic, that the correction ends up being. Alternatively, what you could do is do the second order Rouse-Scott adjustment, which is equivalent to a Satterthwaite adjustment, which basically says this. Have the expected value of this and the variance of this be the same as a chi-square RC find what the adjustment would be, and put this with X squared S. So one could approach it that way. And this halfway adjustment doesn't work too bad. Not as good as my Bootstrap approach, but it doesn't work too bad. So the next few slides kind of discuss these approximations. Now, as a tip for some of you who are perhaps thinking about a job in academia, especially if you're thinking about going to an academic department where you actually do research, where you're not just, let's say, doing teaching only. It is good to show that you can do more than, let's say, just like a simulation study, that you can actually derive stuff. And so in my job interview presentation, I purposely put some of the details of these derivations here. So we don't need to talk about them here. Okay, now finally, 45 minutes later, we get to the Bootstrap. This again is another example that in this class, it can be difficult to teach because if we want to get into interesting application of the Bootstrap, it often takes a lot of prep work to understand the actual statistical method before we can actually apply Bootstrap. Okay, so I want to use the Bootstrap to estimate the sampling distribution of X squared S. Now remember, this is Bootstrap hypothesis testing. So I need a way to do my resampling under the null hypothesis. Here's how I can do it. First of all, I decompose the data into binary item response vectors for the row and column MRCs. In other words, every individual has this, as we saw before. In terms of the Kansas farmer data. Every individual has this. And I guess I actually did have that on the slide. Sometimes I need to look at my notes. Once I have that, then I'm going to take B resamples. I didn't use R, I used B. B resamples the size in it by randomly selecting this W and this Y independently. So why is this under the null hypothesis? Because I'm working with W and I'm working with Y independently of one another. Remember what the null hypothesis says. W1 is independent of Y1. W1 is independent of Y2, and so on. So I'm taking these vectors of W's and Y's independently of one another, resampling them. So I resample a W, I resample a Y, and I stick them together, and that's my first observation of my resample data set. Go to W again, go to Y again, put them together, that's my second resample. Think about how this is very similar to what we did for the Pearson chi-square test for independence. The main difference is that we didn't have vectors. We didn't have vectors that we were working with. We had, let's say, a W1 and a Y1. Otherwise, it's the same idea. And what this does then, it preserves then the possible dependence that occurs between the W's and the Y's themselves. This is actually resampling under a special case of the null hypothesis. Specifically, remember that joint table? This is resampling under if we had independence in that table. But I can do that. It's under the null hypothesis.
The marginal table implies it.
Joint table independence implies S1. Now, it's always been an interest to me to determine, well, I shouldn't say this would have been. I actually, in my research, I did some simulations to look at, well, what would happen if in my true data I did not have joint independence, but I did have SP and Y, and everything was still working out. But it's always been of interest to me to look at it in a more mathematical context to see if there is maybe something I was missing in just a simulation study. So now for each resample, let's calculate my test statistic. Let's call it x squared SB, and then I'm going to put a star on it to say this is for the B3 sample. And then let's calculate a p-value. In other words, the proportion of these x squared stars that are greater than x squared. So simple proportions. In your project, I would like you to still use the r plus 1 in the denominator, and then the numerator you would have 1 plus the number of these x squared stars greater than x squared. You're going to get about the same result. Let's just be consistent with whatever it does. This is what Efron Tibshirani's does on the Bootstrap, so that's why I just did that. Okay, so there you go. There are other approaches, though, that you could use in this case with respect to the Bootstrap. These are what are called P-value combination methods. P-value combination methods are sometimes used in a meta-analysis setting. Well, what we want to do is this. We want to somehow combine p-values from each of these x squared s sub ij's. So like in the Kansas Farmer data, I'm going to have 20 of these x squared s sub ij's. If I use chi-square 1 approximations with each, I'm going to have 20 different p-values. So since those p-values represent evidence against independence for a combination of w and a combination of y, well, maybe we could just work with these p-values, combine them together somehow, and form a test statistic like that. In particular, how about we could simply take the product of the p-values? Sure, why not? Notice how this would be equivalent to taking the sum of the logs of the p-values. I could also maybe take the minimum p-value. That kind of makes sense. You know, take the minimum of all of them. What we call the statistic p tilde. Now the problem, though, here is since each of these p-values are correlated with one another, I can't use what are the usual methods for p-value combination methods, which would assume independence between the p-values. So the Bootstrap comes to our rescue. So how can we do it? Well, resample in the same way as before. Calculate p tilde star now for every single resample. And then my p-value is the proportion of these p tilde stars less than p tilde. Why do I have a less than there instead of the greater than that we had previously? We want the extreme, because remember, a small p-value indicates evidence against the null hypothesis in the general setting. So that's why we have this. And again, remember, all the Bootstrap is doing is replacing what we normally think of as a continuous distribution now with a histogram. And we look at where my observed test statistic now falls on this histogram to get a judgment of what's extreme. Other approaches, let's get to the actual data. So I took 10,000 resamples here. And we can just focus on the Bootstrap approaches. We can see that all of them have good evidence against SPMI. So we reject SPMI here. There's various ways in that one could follow up to determine what combinations of the W's and the Y's cause the rejection. So some of these methods involve the Bootstrap, some don't necessarily involve the Bootstrap. I'm going to skip over that because it's not in the project. Okay. Let's see now. That takes us then to page 31. Now there are so far what I've been talking about is non-model-based approaches, but there are model-based approaches that one could use to do similar tests. I won't get into to all of them. I won't get into them here. Some of you might have some experience with the generalized linear mixed model. This would not work out well here in many problems. One of the reasons is because with the generalized linear mixed model, you're assuming positive correlation between different responses that, let's say, an individual would contribute to the survey. But you can imagine a setting with this kind of data where you do not have positively correlated responses. Thus, a generalized linear mixed model would not work well. There's other reasons why generalized linear mixed model work. That's just some reasoning behind it. You can use GE approaches as well. They typically, because they use wall tests, it takes a very large sample size for them to work well. Okay, let's get into some simulations. For the project, you will actually replicate a small portion of my simulations. So in this kind of a setting, what we're looking for is, well, okay, so we have this method to do it. We expect it to probably work out because we know, the Bootstrap works. But what we would like to know is that for a fixed sample size, what's going to happen? How low of a sample size can I go before maybe the method breaks down? So since I'm involved in hypothesis testing here, I want to estimate the type 1 error rate. So, you specify a type 1 error rate of 0.05. But for a hypothesis testing method, is it really, truly 0.05? Maybe not. And so, when you're doing research, statistical research, proposing a new hypothesis testing method, you need to check, is my type 1 error rate that actually occurs the same as what I state? This is very similar to when you're working with confidence intervals. You have a true confidence level, what truly the coverage level is, and you can compare it to what the stated confidence level is. So if you state 95%, is your interval really truly 95% or not? So I want to calculate an estimated type 1 error rate, portion of data sets in which SPMI is incorrectly rejected, where I'm going to actually simulate data assuming SPMI is true. The way I generated the data was through using a correlated binary data algorithm. There's many of them out there. This is my favorite. We don't need to get into the details behind it. It's actually for a project we're going to use a different one. We're programming into R. So in this setting, what I need to do is specify what these marginal probabilities are. So this is, for example, the probability W1 is equal to 1. Notice I do not need to specify pi sub ij, because under the null hypothesis, this is true. My odds ratios, my measure of association then between each W and Y pair is 1, meaning I have independence in other words. In other words, I have this. We don't want to think in terms of odds ratios. But however, I'm not going to specify the specific dependence between WI and WI prime pairs. These could be anything. Maybe I have high correlation between them. Same thing with the Y's as well. Maybe I have high correlation between them, or large odds ratios, if you want to think of that way. So here are the settings that I help console for each simulation. Nominal type 1 error rate of 0.05. That's the goal. If my estimated type 1 error rate is close to it, my method works. I'm going to generate 500 data sets here. For each data set, I'm only going to take 1,000 resamples. How many total data sets am I actually simulating? 500 plus 500 times 1,000. I can't even write. Which would be, let's see now, 500,000, 500. That's a lot of data. And you have to calculate the statistic every single time. Again, I was using computing power from 2002. 2003. Yeah. well, what if these methods are working, and if I'm actually just originally starting off with 500 simulated data sets, how do I know if my estimated type 1 error rate is close enough to the 0.05 level to indicate, yeah, it seems like this is working? And this is where a nice little normal approximation to the binomial occurs. Take 0.05 plus or minus 2 standard deviations. So roughly 0.03 to 0.07. If I have an estimated type 1 error rate inside of there, great. If I have one outside, then I'm starting to worry that maybe my method isn't working. Just a side note here. Many people who well, I often see this, well, I shouldn't say often, I sometimes see this in research papers where people will take 10,000 data sets and simulate that. Not necessarily with respect to Bootstrap. That's what they're doing here. Is it going to affect this that much? Your end result? You might get down to about 0.06 to 0.04 to 0.06, but it doesn't really affect that much. So when you're actually doing research and if you're doing stuff like this, taking a whole lot of data sets is really not that important. Often 500 is enough. I especially bring this up because working with even my students, sometimes they want to take more. No, you don't need to take that many. So I have a trellis plot on the next slide that illustrates the results that I got. Trellis plot. Have we talked about trellis plots in here? Another common term for trellis plots is a coplot, conditional plot. It allows you to plot multivariate data in a smaller number of dimensions by conditioning. That's where the co-plot comes from. By conditioning on particular values. And trellis plots are great tools for summarizing simulation studies because simulation studies are basically, you get multivariate data from there. Estimated type 1 error rate. What's your sample size? What is various settings that you're using in the simulation study? And here are some of the results. Okay. So the conditioning happens here. Or let me hold off. And let me get a new pen. So on the x-axis, I have estimated type 1 error rate. But remember, the goal is 0.05. So that's why you see vertical lines at 0.05. The vertical lines around it comes from that approximation, at 0.03 to 0.07. So stuff inside there in terms of estimated type 1 error rate show my method is working. On the y-axis, I have my particular methods that I'm interested in. And let's focus on Bootstrap. So for a 5x5 marginal table with a sample size of 50, here's my x squared s. Great, it works. Here it is for Bootstrap product of the p-values, Bootstrap using the minimum of the p-values. And you can see, let me do some erasing here. And you can see that my method is working. This corresponds to a particular situation where the odds ratio between Wi and Wi prime, that odds ratio, is set to 2. The same thing for the y's as well. So I have moderate association. X squared s with a chi-square RC approximation. This is that naively you're assuming independence. This actually ends up being a first-order Rao-Scott correction as well. Look at what's happening here. You're outside that range, indicating you're not holding the correct size of the test. Look what happens when I jack up the correlation. It breaks down. And you can see that consistently through all my simulations. This method, referred to as the Bonferroni, often ends up being too conservative, meaning that you start having points below the line. The second order Rao-Scott correction there often has has small problems too for smaller sample sizes. So this is a trellis plot. It's multivariate data in terms of I have odds ratio settings. Notice what I'm doing here. I'm conditioning on the different odds ratios. Also, I'm looking at different sample sizes in the same plot as well. Trellis plots, again, are a great way to summarize simulation studies. I don't know why people don't use them more. Unfortunately, what you often see in papers are just simple tables summarizing everything. And you think, for statisticians, we can come up with a better way to summarize results by than just a table. One of the problems is that editors don't want to take up the space with putting plots in it. Yeah.
So if you're looking at more than just the type 1 error rate, would there be any reason that you might need to use more take-home samples with your simulation study?
Not really. And what's actually happening here is that, even though I'm just taking 1,000 resamples, look at all the resamples I'm actually taking in the end, and things kind of just average out.
Yeah, I mean in terms of the 500 data.
Oh,
So,
no.
Okay.
Well, I mean, typically, you're always in a type 1 error setting. You're always going to be working with small alpha. And so that range that you're going to have, that plus or minus 2 standard deviations, is going to be relatively small. I guess I cannot think of any particular setting where, let's say maybe I'm doing a power study, and perhaps I'm shooting. I know, for example, my power has to be 0.5. I know my method's working if I have a power of 0.5. I don't know of a particular setting where that would occur. But if that was your goal, obviously your range would be wider. Does that help you?
Yeah, I mean different outcomes, like in terms of like estimating like the bias of some other grammar. I don't know.
Well, at least right now, I cannot think of a specific instance, but if you want to discuss it more, we can. Okay, just a little summary. I also look at power. So in a power setting, of course, now you allow for dependence between a W and a Y. And, of course, you would exclude from a power study those procedures that do not have the correct size. It wouldn't make sense to look at power, especially if they're rejecting too much when you know the null hypothesis is true. And there's not one best procedure. Okay, let's see if that concludes. I think it does. So, that's the end of the presentation. Let's talk about the project. So we get started on it this weekend. I'm sure all of you are anxious to do that. Let me just mention, too, because I haven't said this yet, you do need to read this paper. I do want you to read my corresponding paper. After my presentation here, the paper is going to be a lot easier to read, but you should still read the paper. Okay. So the purpose of this project was for you to reproduce some of the results in the paper, which then correspond to some of the results that we saw in the presentation itself. So right now it's due Tuesday, November 6th, so you have 12 days to work on it. So 1A, create a function that calculates x squared sub s sub ij. I didn't say it right, but you know what I mean. The nice thing about this, when you do this, you know what the correct answer will be with respect to the Kansas Farmer data. Kansas Farmer data is on my website. I'll actually show you that. It's just a comma delimited file, and this is what it looks like. So the first 4 columns are the W's, the last 5 columns are the Y's.
So it's already in the W and Y.
Yep.
Okay.
Yep. So it's already in that form. There are 279 different rows. Okay. So I recommend, like for example, using the chi.su.test function to compute these Pearson statistics for every W and Y combination. So you might think of some loops to loop over every single pair. Then do the Bootstrap p-value for the SPMI test. Specifically, I guess unfortunately I didn't say this very well here. I want you to use x squared s. So 10,000 resamples. There's a C number. You might remember when we were doing a Pearson chi-square test in this class with respect to Bootstrap, I said you have to worry about if maybe you no longer have a 2x2 table anymore, and so maybe you should construct some kind of check. Save you time. Don't worry about that here. At least I did not have that problem with this C number. Also, a little helpful hint. It was a pain to try to get everything to work with the boot function, and so I just abandoned that approach. So I did it without the boot function, which, in a research setting, often that's what you're going to have to do. You can't necessarily rely on canned procedures to do what you want to do, or canned functions. So I recommend not using the boot function for this. Part C, now do this for the two p-value combination methods. I actually wrote one function that does x squared s and the two p-value combination methods. It's up to you if you want to separate stuff out. I wrote one function that did it because I want you to use exact same resamples. Part D, do x squared s p-value combination methods now using a permutation test. We're going to talk about permutation tests, yeah, so you'll learn how to do that, or how to do something like this next time. And it's going to be very easy, very easy. And lastly, I want you to do now a very small portion of the simulation study. It's in the paper. So in the paper itself, there is table 5. And what I have highlighted there, so I couldn't get the publisher to put my plot in there. And so I had a table. And if you do a table, though, it is one, I guess, thing that's nice to do is you actually could use shading to show places where you're not holding the correct size, meaning that you're outside that 0.03, 0.07 boundary. And so that's what I was able to do. It helps you when you look at the table. You can see, yes, indeed, this first method that I have up here is not working very well. So, in this particular situation, then, we see here is pi 1 dot, pi 2 dot, so 0.4 and 0.5. Pi dot 1 is 0.3. Pi dot 2 is, pi dot 1 is 0.2. Pi dot 2 is 0.3. We're going to work with the 2x2 table. The odds ratios within a W and within a Y are going to be set to 2. I'll tell you what those are in terms of Pearson correlations. Sample size of 100. And your estimated type 1 error rates should be similar. They won't be exactly the same because you're not using the same resamples as I did. In fact, I use SAS to do all this. I did my whole dissertation pretty much all in SAS. So obviously R wasn't very prevalent at the time. So to help you out then, first of all, how can you simulate data? We're going to go over just for a few minutes, but I want to at least get you started here. How can you simulate data in this setting? Well, there is a function R called EP that allows you to simulate correlated binary data. That's what we have. It's in a package you need to download, MVT binary EP. The EP stands for Emmerich and Piedmonte, which came up with a method that was an American statistician in the early 1990s that this particular function emulates. And basically what it does, it actually uses a multivariate normal distribution to help generate these correlated binary outcomes. We're not getting into the details. The details are not important for us. With an odds ratio of 2 for W1 and W2, the corresponding Pearson correlation is 0.169. For Y1 and Y2, for an odds ratio of 2, the corresponding Pearson correlation is 0.1353. And here's the actual way to simulate the data. When I wrote up the project, I forgot to say, well, of course, you need to say library, MVT, binary, EP. You need to specify a correlation matrix. Think of this as a correlation matrix that you would have with a multivariate normal. This is for W1, W2, Y1, Y2, W1, W2, Y1, Y2. Notice how the correlations between the W's and the Y's are set equal to 0. This is under the null hypothesis. The correlations within a Y or within W are set to particular values to simulate, yes, you can have dependency. $500 resample, I'm sorry, I don't know why I used B in this case, but this is 500 different simulated data sets. Each of them are size 100. I'm going to put the results into save.data. The first argument of EP corresponds to pi r and pi c. And in fact, what this ends up being is the mu vector for a multivariate normal. You put in your correlation matrix. 4 corresponds to, you have 4 binary variables, 4 binary variables. 500 data sets of size n, and here's your C number. When you actually run it, there will be an object called save.data $y that contains the simulated data. Let me show you that real fast. Library, MVT, binary. Here. So here are the first 6 observations of the first data set. Notice what it gives us the heading here. This is actually W1 and W2. This is Y1 and Y2. So be careful about that. So once you have that, then simulate data. Show me the first and last data set just to make sure you've done it right. Also verify that indeed the correlation matrix between the data that you simulated matches close to what you use, and that the marginal means are close to what you specified as well. This is a way to verify you simulated data correctly. Part 2, perform the bootstrap now on all simulated data sets. This took me 45 minutes to complete on my computer. And perform the bootstrap on the first data set, and then for all the data sets, it took me 45 minutes. And then do a power. Look at the power, and now we're setting the dependence between the W's and Y's to be 2. Here are the corresponding correlations. You can simply put the correlations into the matrix here where you see the zeros. Sorry, I went over 5 minutes. I'll try to make that up some other time.
Let us out.
Oh, well, thank you. Thank you. Good. Now I don't have to. Are there any questions? Okay. So if you do have questions, please feel free to post them to the listserv and wait until next day to ask. That's it for today.